Welcome back. In this synthetic group question, we're going to start with benzoic acid or benzene carboxylic acid, and we're going to try and come up with a synthetic route that makes this particular alcohol. Now again, the first thing that you always want to do in starting these synthetic route questions is to count the carbons in your carbon skeleton. And so in our starting material, we have our benzene ring, and then benzoic acid contains a single carbon. Whereas in our target alcohol, we have our benzene ring, but we have 3 carbons in our target compound. And so this tells you right away that a carbon-carbon bond-forming reaction will be required at some point during this synthesis. So now we want to think about ways in which we can add, if you will, carbon to the corresponding carboxylic acid. Now, one thing we mentioned in section 12 when talking about carbon nucleophiles is that Grignard reagents and organolithiums do not react well with carboxylic acids. And that's primarily because you have a good source of protons, and that will quench the reaction, even under excess conditions. So that is most likely the first step that we need to consider. How do we prepare something from the carboxylic acid that will be more amenable to a Grignard type reaction or some other carbon nucleophile? And so we know from experience, or from section 13, that we can convert carboxylic acids to the corresponding acid chlorides very effectively using thionyl chloride. And again, this is a very helpful reaction in the sense that thionyl chlorides, or pardon me, the reaction with thionyl chlorides generates acid chlorides, which we know has various pathways that we can take to other functionalities. And so using thionyl chloride in this example to react with benzoic acid will give us our corresponding acid chloride. Our benzene carbonyl chloride. Now, this particular compound, the acid chloride, we can reduce this to the alcohol, but that's not going to help us with the addition of at least 2 carbons to our skeleton. So it's best to be starting to think about carbon-carbon bond-forming reactions that would work well with this particular carboxylic acid derivative. And one should come to mind, one that we specifically discussed with the acid chlorides, and that's the Gilman reagent. The Gilman reagent, if you recall, is an alkylating agent, another carbon nucleophile that can be used to react with acid chlorides and acid anhydrides. And so if we want to extend the amount of carbon in this particular side chain from 1 carbon to 2 additional carbons, we would like to introduce a 2-carbon nucleophile at this point. So we can use our Gilman reagent, our lithium diethyl cuprate, to give us the corresponding ketone. So not only have we formed our ketone, but more importantly, we have increased the amount of carbon in our side chain, in our substituent off the benzene ring. And so now we have identical number of carbons in our intermediate structure, intermediate product, as we do in the target compound, our final alcohol. So from this point, what we need to do is reduce this particular ketone to the alcohol. And we saw that there's 2 ways in which we can carry out this reduction. We could use sodium borohydride in any protic solvent, water, methanol, and that will reduce the ketone to the corresponding alcohol. You could also use, in 2 steps, lithium aluminum hydride and follow that with a water wash. So either would be acceptable. So here we have again a 3-step synthesis. We started with a carboxylic acid, and what we were after was not just the reduced carboxylic acid, but we wanted an alcohol that also had 2 additional carbons attached to what would be that original carbonyl carbon. Carboxylic acids are not the easiest to work with carbon nucleophiles, so converting this to an acid chloride is an important step. This allows us to then carry out further reactivity on this compound to include and install these additional carbons. Using the Gilman is the most effective way to do this. As we've mentioned in the past, it's a more selective alkylating agent than using a Grignard or organolithium. And just to highlight that point, if we were to have tried to carry out the same strategy using ethyl magnesium bromide, which would have been, plausible, at least as a first step, the end result, unfortunately, would not be this particular ketone. And that's because it's very difficult to control the reactivity of the Grignard reagent in the presence of this acid chloride. It will react in a manner to form this particular ketone, but then it's very difficult to control this particular Grignard from not reacting with this ketone to form the corresponding alcohol. So you would have ended up with the following alcohol as a result. So yes, you would have formed one carbon-carbon bond-forming reaction to give you the ethyl group, but you would have formed a second one as well. Again, very difficult to control. Even if you're just using a single equivalent of the Grignard, it's very difficult to control the reactivity with the ketone that's generated in situ. It will continue to react, and so at best you'll end up with a mixture of products, some of which might be the ketone, but definitely you're going to have a lot of alcohol present in which 2 R groups are installed at that original carbonyl carbon. So although this would seem like a plausible route to produce this alcohol, you're going to run into troubles in forming quite a bit of this as well. And so it's important that your choice of alkylating agent is done well, and that using the Gilman ensures that you're only going to have one equivalent, if you will, of that new carbon-carbon bond-forming reaction. So you're going to only have one nucleophilic acyl substitution for the chloride leaving group. You're going to have one carbon-carbon bond-forming reaction to form what ends up being this 3-carbon unit of your side chain. So just a point to make that, yes, we may have a variety of alkylating agents that we can use, but we have to be careful in our selection. If we were to use organolithiums or Grignards in this example, we would have ended up with the wrong target alcohol. And so it was really important to identify the Gilman reagent as the ideal alkylating agent to get us to this ketone, which then we could reduce using either sodium borohydride or lithium aluminum hydride to give us our final alcohol. So if you have any questions about this particular synthetic group question or any others that you encounter in your studies, by all means, please send me a message or an email. Thank you.